I'm not a co-host. I don't know if it's important, but it's a pleasure to have Esmail Arasteh Rad to talk about zeta functions for the moduli of G-Shtukas. It's hard to introduce Esmail. I don't know if I should say he's from Munster University, from Taiwan, the institute, or IPM. So all three places. So thank you very much.
Mamnoon Hadijan, thank you very much. I need still your permission, I guess, to share my screen.
Well, I'm not a co-host. I cannot give you permission, so maybe Ilhan can.
Okay, good. Yeah, so actually, so what am I gonna talk about is a joint work with Tuan Negodak, and also a series of joint works with Urs Hartel. So here I have provided some sort of outline of my talk. So it is like maybe the most sophisticated page of my talk. And then you can imagine. So yeah, that's because I'm not that kind of well-ordered people. So I might start with the end and then go backward. I always take this kind of note for myself. Anyway, so, okay, so regarding my title, so the title of my talk, so I thought that maybe I should begin with the following quotation from Fermat, so that's the famous one. Yeah, so there's not enough space in the margin, so yeah, okay. Okay, by the way, so I have to thank lots of people. Of course, I mean, people in the organizing committee, so they did a lot. I'm grateful also to Professor Diej for yesterday opening talk, and I mean, that was kind of very promising one. And also to Ilhan. So Ilhan did lots of things. So we are like, I'm at least extremely, I mean, I'm not sort of capable to express my sort of gratitude to him. So he did lots of things, and in a very kind way, and also in a very kind of careful way. So these are hard to be like joint. So when you are very careful, then you cannot be that kind. And when you're too kind, then you cannot be very careful. So you need to do some sort of cruel things sometimes. But he like balanced everything. So it was amazing for me. And there's one further person that I'm gonna thank. John Ozan, so I'm gonna explain something about him. So first time we met, so the meeting that I had with Ilhan some years ago in Istanbul was relying on some other meeting with him in somewhere in mountains in North Spain. So I have a photo from there here. And I found him while he was observing birds. Yeah, and like I mean photographing from birds. So he's a young mathematician from Turkey, and he actually introduced me to Professor Ikeda. Here I have like some photos from that hikings we had there. And he was also practicing some sort of yoga of recognizing birds out of their songs. So this was also very fascinating. And I mentioned to him that this is tightly related to your interest in mathematics, because we are almost doing the same thing. So we hear some sort of songs. So there are sometimes there's, for example, cohomology theories, and we have to like recognize the bird outside, and that's like the hidden geometry behind this sort of harmonies. So, and he was like practicing that yoga. And while, I mean, once I mentioned to him that I mean, your both interest in mathematics and to birds are somehow tightly related, he mentioned to me that maybe I have to talk with Ilhan. Yeah, that was quite fascinating. And by the way, his name was also very fascinating to me. So Can Ozan. So Can in Persian means spirit, and Ozan means sher, means poem. And Can, which kind of, I mean, rich heritage, I mean, cultural heritage it would be that they give such a name to their children. So spirit of poems or something. Anyway, yeah, so this is like, I mean, our births, and then we have sort of incarnations inside different categories. So we have geometry, and we have different sorts of algebras that it gets like, I mean, this geometry like manifested inside these sorts of categories. And then when you are doing poetry, then perhaps you want to enrich your language and come to some sort of language that would makes you enough capable to speak about the beauty you see here. And Grothendieck was one of these poets, so he introduced the category of motifs, or he, like, I mean, very much expected that such a beautiful dream like comes at some point to the light of the day. That, I mean, makes one capable to, like, I mean, talk about the whole beauties of all these bears we have upstairs, but we are unable to see them or talk about them. And therefore he was seeking such a nice language for making him like capable of doing that. So his construction was very clever. So this was like a basic idea he had for a long time already, and actually it's very amazing. So he had this sort of idea that the notion of function is sort of misleading notion. Yeah, I mean, he used that very often. So he replaces function with other things. So even once you try to teach functions to like high school students, you see that they find it some sort of unnatural thing. So they see that they are not like, I mean, they are not sort of symmetric things, and therefore, I mean, and Grothendieck was, I mean, able to think of like a children. So he was quite flexible to everything. So he like replaced the notion of function with sort of correspondences, which are more symmetric sort of creatures and more like poetic type things rather than like strict sort of notion of function. So he replaced the functions between x and y with the correspondences between x and y. Okay, so here you have to introduce some sort of equivalence relation. So once you like gives this sort of things, you come with some sort of prototype version of the motivic categories one wants to deal with. And then he proposed some sort of conjectures that, I mean, basically are like demanded to come up with some sort of semi-simple abelian category. So these are called the standard conjectures. And then so other people, like, I mean, these conjectures are like, I mean, far unreached. So other people found some sort of ways to like work around these conjectures. So one was, of course, I mean, Delhi, and the other one is like the work of Janssen, so who proved that with, I mean, our finite fields, and once you take this equivalence relation to be numerical equivalence, then your category of motifs is abelian semi-simple. So it had, I mean, the proof was quite elementary, and somehow, like, I mean, people did not expect it. But then, so you have to like introduce realization functors. And these are like problematic because they are relying on some sort of difficult conjectures. And then also other people came. So for example, one should mention Voevodsky, who proposed some sort of derived version of these motivic categories to handle more general schemes. So to handle sort of mixed creature things. And then also, I mean, you have the work of Szyczynski and Deglis, who provide this sort of environment for general X. search of general X. Okay, so these are all stories on the number field setup. And as you have already heard from the beginning talk today, so there is like a picture of a function field which mirrors all these things over there. Okay. Okay, here, so we replace Q with some sort of curve of a finite field. And then there are candidates for the notion of motive in the other side. So maybe it was initiated by the work of Drinfeld. So a very prototype of this sort of creatures are Drinfeld models. And then, okay, then this sort of things has been generalized to higher ranks, to higher dimensions. So they are called Anderson T motives. They are basically some sort of semi-linear objects. So you have your ring of polynomials, and you have some, say, A field, L, you have a characteristic function, and then an Anderson T motive is such a tuple of data consisting of some locally free AL module, some free AL module, let's say, of certain rank, and then you have a Frobenius connection, which relates the Frobenius pullback of M to M itself. Yeah, and Frobenius pullback would mean that, I mean, the Frobenius morphism is like identity on the A, and it's like raising to the power Q on the second factor. And you use that to pull back this guy, and then you relate these two things. So I call this sort of creations as Frobenius connections. Yeah. Okay, and then you have some sort of further requirements that some
Excuse me, what is AL?
AL is like A tensor L over Q. So you just take
L of T.
Yeah. And then you have like to impose some sort of boundedness condition. So you require that some power of your, I mean, the power of the graph of your characteristic function kills the co-kernel of it. So it is like, I mean, yeah, I mean, you have certain poles here, and then it should be like controlled by something, some power of you. I mean, it is only allowed to have these sort of things along the graph of these characteristic sections. Okay. Then there's Tellman's construction of the category of motives over function fields. So he like passed to the rational morphism. So he passed to quasi morphisms, let's say, and he then takes the analog of the Lifshitz motive, and then he simply inverts that inside the category to, like, I mean, produce something more close to the analog of the Grothendieck's category of motives. And then, okay, so this category is a Tanakian category, and it admits realization functors also. And you have a non-neutral fiber functor also. Here, so again, there's a missing L. So this functor goes from the category of motives, Tellman's motive, and it goes to the QL vector spaces. So there is a missing L here. So there's Q sub L vector spaces. Okay, so far so good. Yeah, but still, so you might need to work with multiplications in some sort of extensions of your polynomial ring of polynomials. So, and also, okay, so after all, at the end of the day, we want to geometrize our category. So we have to treat like the motives of a general base. We have to come up with some sort of parameterization of our motives. Okay, I mean, to handle this kind of problem, so I mean, almost easy. So you have to add the place at infinity. And then you come up with some curve, a smooth projective curve, And then you replace your locally free module you had over A or over FQT with some sort of vector bundle over your curve. And then you want to try to extend your Frobenius connection over your curve, but there's a problem of like balancing order of zeros and poles and that kind of things. Then you have to like do it in the following way. So you have to invert further Carlist motifs. Okay, and this corresponds to introducing further characteristic sections. Okay. Well, so this way, so you come to the following definition. So you take some sort of characteristic places on your curve C, and then take some base scheme S. Then a C motif with that sort of characteristic is a tuple consisting of the following data. So you have a locally free sheaf or a vector bundle, let's say, over C cross S. And then you have your Frobenius connection defined outside these characteristic places. So you have to remove the characteristic places, and then you allow the Frobenius connection to be defined outside that. And then you have your morphisms. So morphisms are such commutative diagrams. Yeah, morphism between two C motifs M and N are such commutative diagrams, which is like defined generically. So you have to pass to the generic fiber. So it's only defined over the generic fiber, and it corresponds to the fact that we are like treating the coefficients in Q, let's say. Yeah, I mean, we extend coefficients to the rational, let's say. Okay, so then one can show that.
Excuse me, can you go back to the previous slide? So tau is the Frobenius on M, and you want it to be an isomorphism away from the characteristic sections, right?
Right, yeah.
Okay, thank you.
Okay, so then you get some sort of category, and it can be shown that it's Tanakian. It admits some non-neutral fiber factor, and you can prove that it's semi-simple. The proof is quite similar to that of Janssen. So one looks at the endomorphism algebra corresponding to that and looks at the Frobenius inside. The only issue here is that perhaps, okay, so you have that sort of things over any finite field, but here you only can, like, I mean, argue, we can only prove after passing to the algebraic closure. Oh my God. Okay. Okay, for this category, so you can also establish realization factors, you can prove Tate conjecture, and also you can like formulate Honda Tate theory. So it means that there is a like analog for Weil protorus, and that parameterizes the quasi-isogenies. Okay, so let me remind you that in the number field setup, so you have moduli of, I mean, you have Shimura varieties which appear as moduli for, let's say, abelian varieties, or in, I mean, more generally as a moduli for motifs. So in the function field setup, so you might seek something that appears as moduli for motifs, and this is gonna be the moduli for G-Shtukas. Okay, that I'm gonna explain that. So you have your category of, okay, first of all, let me remind you about this guy. So you have the stack of G bundles over your curve C. So you fix the smooth projective curve C, and then you have this stack whose S points parameterizes the category of G bundles over C cross S. So by the way, I mean, stacks are sort of natural creatures. So the schemes somehow would forget the symmetry you have. And stacks are just some sort of schemes who remember this. Yeah, they remember the symmetry you had, because I mean, schemes are like, I mean, are kind of sheaves whose values are on the sets. I mean, come inside sets, and there you don't have like I mean, you forget everything. But once you keep track of the symmetries you had, you naturally come to the definition of stacks. In that sense, I mean, stacks are not strange sort of creatures. They are more natural things to think of. Okay, so then this stack of G bundles, I mean, one can show that this is an Artin stack, locally of finite type. So this is like, I mean, a classic result of parent for G reductive, I mean, split reductive, and then for parahoric, it was proved by Heinlutz. But I mean, one only requires flat affine group schemes. I mean, one can prove it in much more, I mean, general setup. Okay, then a G-Shtukas over some scheme S is a tuple of data, yeah, and consisting of the following things. So you have a G bundle over C cross S, and then you have sort of characteristic sections, and you have again like a Frobenius connection, so a morphism between the Frobenius pullback of your G bundle to itself, which is defined also in certain characteristic places. Okay. Okay, so we introduce this sort of notation for the stack of G-Shtukas, nabla n h1 cg, and the reason comes from something like, I mean, geometric Langlands or something, for, I mean, the thing behind this notation, behind this strange notation. Okay, so one can prove that this moduli stack is the linear int the linear Mumford. So you have to impose sort of boundedness condition, and then you come up with sort of the linear Mumford stack. So you can visualize that as sort of int guy, and you can formulate some sort of int structures on it.
So where does the int structure come from?
So from the boundedness condition. So you all the time, so you have poles and zeros. Yeah, you would not get something of finite type anyway, unless you, I mean, impose sort of boundedness conditions.
And on what? On the so the bounded condition and the cokernel of the Frobenius somehow?
Exactly. I mean, yeah, somehow on the cokernel of the Frobenius. Yeah, you have to. I mean, we have already met these sort of things. Yeah, I mean, these are similar sort of things. Here you have. So I would come to that maybe later, but I mean, we would, I mean, talk about boundedness conditions later.
Okay, thank you.
Then you have functoriality. Yeah, to CG, so you can assign some stack, some in the stack, and this is like this assignment is functorial in the sense that, I mean, both on C and G, but on C is somehow complicated. I mean, needs some work, because then you have to like interchange this G also when you replace C with some other, let's say with C prime. But with the other factor, with G, it is easy. Yeah, so it is simply comes from, I mean, usual extension of G bundles to G prime bundles. Once you have a morphism from G to G prime, so, and you have a G torsor, once you have a G torsor or G bundle over C cross S, you can, like, I mean, twist it up with G prime, and then you would get some G prime bundle. So it induces a morphism in here. Yeah. Okay. And in particular, so once you have a G-Shtukas, you can, I mean, view it, or you can assign to it a morphism from this representation category of G to your category of motifs. In that sense, you can see, yeah, I mean, this category of, so once you have a representation, via this functoriality, you can produce some GLN Shtukas, and to that GLN Shtukas, you can assign some motif, because, I mean, GLN bundles are vector bundles. And in that sense, so you can see a G-Shtukas as sort of a motif together with a G structure on it in the Tanakian sense. Yeah, in this sense, so the moduli of G-Shtukas is a moduli for motifs with G structure. So these are like very, very natural sort of constructions. Natural analogs for Shimura varieties. Okay, so it goes to the category of motifs, as we have seen. And there we have realization functors. Okay, so therefore you can assign a realization, so to say, étale or crystalline realization to your G-Shtuka. Okay, so again, so we had our characteristic places on C. We have our moduli of G-Shtukas. So we restrict our characteristic sections to certain places on our curve, to certain characteristic places on our curve. And then, well, you would get étale realization functor because you can see, you can view your G-Shtuka as kind of G motif, which goes to the category of C motifs, let's say. I mean, a functor from rep G to the category of C motifs. And then you can like evaluate it. You can take the étale cohomology realization. Then you would get a representation of the fundamental group. So you get a Galois representation out of, I mean, you can cook up some Galois representation out of your motif. Yeah, I mean, you have your G-Shtuka. You assign to that, you view it as a morphism from rep G to category of motifs. You take the realization, you take the étale realization, you end up in here. So this way you can assign an étale realization to your G-Shtuka. Okay. Okay, once you have étale realization, then you can do level structures. Again, we do it in a Tanakian manner. You have your étale realization. It is a functor from rep G to the category of Galois representations. And you have your like forgetful functor, your neutral functor of rep G, and you can like trivialize it in a factorial way. So you look at the tensor isomorphisms between the between the étale realization of your G-Shtuka and the forgetful, the neutral functor, let's say. Okay, you get a set on which you have two different operations. So this was like étale realization functor. Therefore, on that, you have the action of the fundamental group or the Galois group you have. It operates on this factor. And on the other side, so you have Tanakian formalism. So the group G itself operates by like interchanging this omega naught by the Tanakian formalism. So you get a bi-action of this guy on this set. And once you like fix some compact open subgroup of the adelic points of your G, then you can do the following. So you can take some orbit under this H, which is also invariant under your action on your Galois action on the other side. And this is called level structure. So it's a very natural way of defining level structure in the Tanakian sense. It is like an H orbit invariant on also the other action by the Galois group inside this set. Okay, so we have defined what étale realization functor is so far, and we also define level structure by trivializing the étale cohomology. And then we come to the crystalline realization functors. Here I have to like first define what loop groups are or remind you about it. So we have some smooth affine group scheme over formal disk, and okay, this P also again denotes the generic fiber of that, and I have also the punctured formal disk, let's say, then you can define the following functors, the functor of positive loops and P, in the following way. So the points over R are simply the points of P over the disk, over the formal disk extended across R, the completed product with R. And similarly, you can define the group of full loops of P, which are like points of that over R are points of P, but after inverting Z. Okay. And you can do the further thing also. You can, one appears one operates on the other one. So this is like a subgroup of, group of positive loops lies inside the group of full loops. And then you can form the following functor, which sends R to such quotients, and can be shown that this is like representable by some sort of variety. So it's called affine flag varieties corresponding to this P. And just let me just mention that this group of positive loops also operates on these affine flag varieties by the action you have from the other side. So you have already killed, you have already passed through the quotient under the action, let's say from right-hand side, or I don't know, from the left-hand side. And then you can still look at the orbits under the action of the L plus P from the other side. Then one can define local G-Shtukas. So these are actually over category of crystalline. This produces the category of crystalline realizations. So these are that sort of tuples of data. Okay, first you fix some S in nil K zeta. So you have to introduce some zeta. And then a local G-Shtuka consists of the following data. So you have L plus and tau hat. So L plus is an L plus P torsor. So it's an L plus P bundle, if you want, over S. And then you look at the associated full loop torsor associated to this positive loop torsor, and you define your Frobenius connection over that. So in the sense that once you have a positive full loop torsor, so you can assign to it a full loop torsor, because you have like such a natural morphism. Therefore, once you have this kind of thing, so you can also pass to the full loop torsors, and you define your Frobenius connection here. Okay, good.
So what was P? P was the affine group scheme?
Well, so P is like a smooth. Okay, we can also relax that. It is at the moment, for definition of G-Shtukas, you can simply think of some, let's say, flat group scheme over disk, over K double bracket Z, let's say.
Thank you.
Over like formal disk. And this P was like the generic fiber of the other P. Okay. And then you can still define the quasi-morphisms here as such commutative diagrams, which is defined like, after inverting Z, after passing to the full loop torsors. Okay, this provides some sort of crystalline realization category. And then you can construct realization functors, so crystalline realization functors, which like initiates with, you have this category of global G-Shtukas. You fix certain characteristic places on that. And at these characteristic places, you can assign your crystalline realizations, which are local G-Shtukas. The construction is like, what it should be. So you have your G-Shtuka, you pass to the completion along the characteristic sections, you get some sort of formal torsors, so formal P-hat torsors, and then the rest is somehow a little lemma, which shows that that sort of formal torsors, the category of that formal torsors are actually the same as the category of loop torsors. Okay, good. I mean, this way, so you can assign a local G-Shtuka or the crystalline realization of some global G-Shtuka. Okay, so then we have boundedness conditions, which are somehow responsible for so to say, bounding the relative positions of torsors, let's say. Okay, so we do that, I mean, in a very geometric manner. So we take some sort of subscheme of our flag variety. So we first, I mean, we had this zeta in the definition of our local G-Shtuka. So we extend everything across this formal disk. And then we take some sort of subvariety of that, which is stable under the action of L plus P. And we further require that the spatial fiber of this guy happens to be the subscheme of a affine flag variety. Yeah, so it is not a group theoretic definition of the boundedness condition. So there are group theoretic definitions around, but it is also, I mean, well, one can, I mean, show that, I mean, this sort of definition generalizes the group theoretic version. So there are like, I mean, different, I mean, there are examples of boundedness conditions which are, I mean, which are like, I mean, non-trivial in that sense that they, I mean, it's not possible that you, like, I mean, that you, I mean, say that they are like arising from the group theoretic sort of descriptions of bounds, as it is like, I mean, it's like a custom to think of that sort of boundedness conditions. Then once you have a morphism between full loop torsors that are coming from positive loop torsors, so you have a morphism from between two loop torsors, L and L prime, and you know that L and L prime coming from positive loop torsors, and you want to bound these sort of things with this sort of creature, with these sort of things, with these sort of boundedness conditions. So you do the following. So you take a trivialization of your positive loop torsor, and you use this trivialization to, I mean, to go first backward. Yeah, I mean, everything node is defined. I mean, here we have L, this is full loop torsor. So we have to pass to LP here. So we go backward and then we go forward with delta, and then we apply this other trivialization. So this way you get a morphism from S prime to your positive loop torsor. And this induces a point on your flag variety. And then you require that this point factors through your boundedness condition. Yeah, factors through the C hat, which lies here, which lives inside the extension of your flag variety. And this way you, I mean, this is a funny way of bounding things, bounding, I mean, controlling the relative position of loop torsors. Okay, so this way you can also bound local G-Shtukas in the sense that you had your Frobenius connection and you require that the tau hat inverse is somehow bounded in that sense. So you fix the boundedness condition, and then you require the tau hat, which is a morphism between torsors, between loop torsors, is bounded by Z hat. Then you say that the local G-Shtuka is bounded by that guy. And here I mentioned that, okay, some of these bounds are arising from group theoretic sort of things. So this omega comes from some sort of affine Weil group. And yeah, I mean, some of those, I mean, let's say classical ones also, I mean, you can embed that sort of boundedness conditions in here. Here I mentioned that this definition that I just gave is like a naive version of the definition of boundedness condition. One has to work a bit harder. So one has to work with sort of extensions of K zeta, because you have reflex string, and this sort of Z hat might be only defined after some base extension. but it's not important. I mean, one can achieve that. And the other thing is that you can also perform boundedness conditions globally using like Bayes and Greenfeld affine Grassmannian, the global Grassmannian, and then these boundedness conditions happen to be certain sort of subvarieties of the global affine Grassmannian. So one can treat things also globally. Then again, I mean, in analogy with Shimura varieties, you can define sort of G-Shtukas data. So there you have Shimura data, and in the other side of the picture, and the other side of this turntable, so you can also produce something which is called Nabla-H data or G-Shtukas data. Similarly, it consists of the following data. So you have your group G, you have an n-tuple of boundedness conditions. Yeah, I mean, one difference between the construction of a function fields with number fields is that here you have more characteristic places. Yeah, and to control the relative positions along all these characteristic places, you have to take like n different boundedness conditions. Yeah, there you have only some mu, some sort of conjugacy class of some sort of morphism from the linear tori to your group G. Here you have to take n tuples of that sort of things. Yeah, this is like a minor difference, but it's very important sort of difference. This is the thing actually that makes things possible in function field setup, which is like absent still in number vertex setup. Okay, so you have your smooth affine group scheme G. You have n tuple of the boundedness conditions at characteristic places. And you have also your H, which is your compact open subgroup responsible for your level structure. And to that sort of data, you can now assign some moduli stack, let's say, some sort of formal algebraic stack, which parameterizes G-Shtukas together with some sort of level structure H, which are bounded by this Z hat. And this Z hat is very important because it is, I mean, has lots of things to do with Zeta theory and other things. So this appears, I mean, as a very important sort of things here. And you have like, I mean, your level structure and everything is here. And this boundedness condition here means that you have your G-Shtukas in here, and you take the crystalline realizations at the place nu I, you get a local P-Shtukas, you bound it with the boundedness condition you have in here. Yeah, you bound the crystalline realizations of your G-Shtukas. So this sort of notation, so this sort of heavy notation includes all that kind of things. Okay. Okay, then one can prove that the resulting thing, when G is smooth, is a formal linear Mumford stack over your reflex ring. So you have a reflex ring, and this guy is defined over that, and one can prove that it's a formal linear Mumford stack. And one can see that, I mean, one can, like, I mean, refine this H in a way that one gets a quasi-projective scheme. And this H appearing here is somehow responsible for the Hecke operation you have on your moduli stack. I'm not sure that we come to that sort of arguments later or not, but anyway. Okay, now let me just remind you about the Zeta function. So you count the points of some, so you have your X, you have your model for X, and then you count the points of that, and you form that kind of series, and then you define your Zeta function. And then when you do not have a good reduction sort of prime, then you have to work a bit harder. So you have to take care of the same simple trace of Frobenius on the sheaf of nearby cycles to define some simple local factor of your Zeta function. And now we are coming to our question, which is supposed to be the main things in my talk, but I'm not sure how much time is left now. Okay. Okay, now, so we are gonna talk
Have
about
15 minutes.
Okay, good. Okay, so you see, so once you want to think of this kind of thing, so you have to take care of the points. Like you have to do the following. So the first question is that you have this counting sort of things. You have to count the points of your moduli stack over finite fields. And then the other mission is to describe the semi-simple trace of Frobenius on this moduli stack. So the first question is related to something which is called Langlands-Rappaport conjecture. So one has to formulate Langlands-Rappaport conjecture over function fields. And the other question is related to the couple of things. So the first thing is that you have to provide some sort of local model for this guy, to understand the action of the Frobenius on the sheaf of the nearby cycles. So you have to pass to something which is more accessible. And this is somehow related to the theory of local models. And the other thing which appears here is the Heinz-Kottwitz conjecture, test function conjecture, which says basically that the semi-simple trace of Frobenius is somehow the same as the Bernstein center in the Hecke algebra. Okay, so yeah, so first you used your local model theory to pass to your local model, and then you have the Kottwitz test function conjecture, which tells you that you can describe that in terms of Bernstein center. Okay. Okay, so okay, keep all these things in your mind, and then we come maybe back to this later. So here I define local Nablash data corresponding to the local Shimura data. Here you have your group P. You have one characteristic, you have your boundedness condition, and you have some B, so to say, which are the following sorts of things. So P is the thing that we have introduced already. Z hat is a boundedness condition, and then you have a sigma conjugacy class in here. Yeah, in the points of, your loop group, your full loop group over K bar. To such data, you can assign some sort of Rappaport Zinke space for local G-Shtukas, which are like local analogs, local counterparts for moduli of G-Shtukas, let's say. Okay, so you have your boundedness condition. To that, you can, assign some reflex ring, and then you can consider the following functor, which is very similar to the one that Mohammad Hadi defined yesterday. So here again, you consider the tuples consisting of a local G-Shtuka. Yeah, you send S to the tuples consisting of a local G-Shtuka together with some sort of quasi-isogeny, a morphism between Shtukas, between local Shtukas. But this morphism only defined after you invert Zeta, let's say, after you inverting the uniformizing parameter of your reflex string. So you have to invert that. You have to kill that, let's say. You kill the Zeta here. So this S bar means that you take the V of Zeta, or V of the uniformizing parameter of this guy here, of your reflex string. And your quasi-isogeny is already defined there. So after vanishing, after killing the Zeta. Okay, so this parameterizes that sort of tuples of datas. And you require that this morphism, you have this Frobenius connection you have in here, is bounded by Z hat. Okay, so this way. Okay, this way you assign some Rappaport Zinke space for local G-Shtukas to a local Nablash data. Okay, so by the way, so this B, in my notation, this B here, Where is that? So I missed some slides. It looks that I left something off. Okay. Okay, one can prove that the resulting thing, I mean, you can prove some sort of analog of the result of Rappaport and zinc. One can show that the resulting thing is some formal scheme. Yeah, there's a moduli space which parameterizes, which represents the functor we have given upstairs, and that guy is a formal scheme, locally formally a finite type, and it actually lies in here as an int closed subscheme of this guy. And one can show that the special fiber of that is an affine linear Lustig variety. Okay. Okay, so that way you can assign the Rappaport zinc space to a local Nabla data. And then, okay, let's for a moment forget about the test function conjecture. So go to the next slide. Okay, it looks that I have looks that I have changed the topic. Okay, so far again I have to ask you to like keep things in mind, and then I would return to the Rappaport zinc spaces maybe later. Here I stated the local model theorem, which says that okay, so you have a Nabla data consisting of that sort of tuples of data. And then you can make such a diagram, such a roof, which connects the geometry, the local geometry of the moduli stack of G-Shtukas to the product of varieties appearing in here inside the affine flag variety. And then you can even do this better, so you can see that this pi here admits a local section locally for the étale topology on this guy, such that the compositum here, you can, so étale locally for any x, you can produce something, some étale neighborhood in here, such that the compositum here is again étale. So it would mean that the local nature of this guy is the same as the local nature of this guy. And then you have the test function conjecture, or like theorem for parahoric groups by Heinz and Richards in here. So this way you can somehow relate the semi-simple trace of Frobenius inside in here to here. And maybe then I come to this remark, which says that, you can express this semi-simple trace of Frobenius in terms of the Bernstein center inside the Hecke algebra. Okay, so you have similar sort of theorem for Rappaport zinc spaces. One can similarly prove that there is such a diagram for Rappaport zinc spaces. Both morphisms are formally smooth morphisms. This one is even a torsor under certain groups. And then you have étale locally, you have sections such that the compositum is again étale. So the local nature of this guy is the same again as he had. And this again allows you to read the semi-simple trace of Frobenius in terms of the center of the Bernstein center inside the Hecke algebra, which appears in the other side. Okay. Okay, this part was related to the second question, and then we go back to the first question I gave. There you have your moduli of Shtukas, and then you can use your Rappaport zinc spaces we have defined together with some sort of extra data concerning the level structure you have, and you can produce such a morphism. Okay, so, and then you can see that this morphism is invariant under the action of the quasi-isogeny group. So I mean, this I sub G naught. Okay, so you have, let me try to explain it a bit better. So you fix some G naught Shtuka in here, inside your moduli of Shtukas. Corresponding to this G naught Shtuka, you get a morphism from something like this, such a product of your Rappaport-Zinke spaces with some sort of isomorphism sort of things, corresponding to some, I mean, taking care of the level structure. And then you have this sort of quotients. And then you have the action of the quasi-isogeny group of this G naught, self-isogenous of G naught on that. And this morphism here is like invariant under this action. You can perform the quotient. And you can do something further. So you can pass to the completion along the image of this morphism. And it can be shown that after doing that, after you pass to the completion along the image of this morphism, you get somehow isomorphisms of the formal schemes. Do I have this slide for that? I have not mentioned it here. Yeah, here I have done that. So you can pass to the completion somehow along the image of the morphism. And the resulting thing is an isomorphism of the formal stacks. Okay, so far so good. Okay, once you have this source of data, so once you have this source of knowledge, then you can formulate the Langlands-Rappaport conjecture for G-Shtukas. So it basically says that, okay, so you have your knowledge data. To that, you can assign some sort of, well, some sort of stacks, let's say. So this here is somehow the spatial fiber of your Rappaport-Zinke space. Yeah, we had the map before. We just pass into the spatial fiber. So we had this map. Where is that? We have this map in here. We just pass into the spatial fiber of this. And now we are just also taking the disjoint union over all the quasi-isogeny classes of G naughts in here. And then the Langlands-Rappaport conjecture states the following. So it says that, okay, once you are doing that and taking care of all these sort of quasi-isogeny classes inside your moduli of G-Shtukas, you would get isomorphisms. So you would get isomorphisms of, let's say, formal stacks. Okay, so one can do this better. So one can just run not only over the quasi-isogeny classes, but one can do that over the sort of, so to say, I mean, admissible quasi-isogeny classes or spatial ones. So these spatial ones only works when you restrict to quasi-split groups. And you also can relax H, so you can pass to the limit over all these H's. Okay, so the Langlands-Rappaport conjecture now states the following. So you have this functor, which is this functor here, which you take all the quasi-isogeny classes and you form the union of all the sets you have in here. And then you put them all together and you would see that there is like a correspondence, or there is an isomorphism of, let's say, formal stacks between these two things. Okay, so the other side is somehow some sort of creature which is like very much closer. I mean, this is like a group, you have a group theoretic description of the left-hand side guy. Yeah, you have a group.
I just wanted to let you know that your time is over, but I don't know how much longer do you need? How much more minutes do you need?
Maybe just 2-3 more minutes.
Okay, thank you.
Okay, so in that sense, so you can relate the points of your modular stack of G-Shtukas to that sort of group. I mean, you can produce some sort of group theoretic description of these points. Good. Okay, so I have explained these kind of things here. So there is a criterion for admissibility by hair, and then one can also describe a set of isogeny classes in sort of Tanakian fundamental group sort of description. And also you can also take the spatial points as well by some result of Van Kim, actually. Good. Okay, this enables one to count the points. Yeah, once you have a group theoretic description of your points of a finite fields, so you can do the following. So you can count the points in here in terms of orbital integrals of the characteristic function of H and the twisted orbital integral of the characteristic, let's say, function of your boundedness condition Z. I mean, in a very standard way. And once you are doing that, I mean, maybe I have to tell you, I mean, this nabla here comes from like the étal realization of the crystalline realization at the place nu I of your G-Shtukas appearing in your description upstairs. And then this gamma is related to the étal realization. And then you have some sort of volume factor. Okay, so these are like orbital integrals, and these are like twisted orbital integrals. Again here, so the Kotvis conjecture, the Kotvis test function conjecture comes and tells us that we can unfold this twisted orbital integral by, like, I mean, exchanging this function in here with some, exchanging this function here with some other function. And therefore, you can also, I mean, unfold this orbital integral appearing inside. And like, I mean, this provides some sort of counting point method for the points in here. Well, I think this was the last slide. Good.
Thank you very much.
Thanks to you also.
So other questions? Esmail?
Can I ask a question? Since you are a motivic guy, and when I catch you, that's a good idea to ask. So there is this recent theory of Scholze called prismatic cohomology.
Mm-hmm.
Where does prismatic cohomology fit in the theory of motifs? That's I am very curious about. Maybe you know the answer.
No, I don't. So actually, yeah, I mean, well, I don't know. I mean, I can say something, but it might be nonsense. Okay, sorry. Mm-hmm.
Mm-hmm. Amir has a question. Please, go ahead.
Okay, I really couldn't follow talk. It was very advanced, much more advanced that I can understand. But I have a question about motifs in general. You started with the definition of Grothendieck for motifs that works for any field. And then you said that over Q, things are complicated, so we change it to a function field. So as far as I know, motifs over finite fields are well understood, and they form a abelian category, even in the mixed situation. Over number field, the existence of such abelian category is conjectural, but a triangulated category of motifs over number field exists due to Wowodsky's work. I want to know for the function field case, what is the situation? Do we have such a cat? So because you mentioned the C motifs and T motifs of, but you actually went away from the original definition of Grothendieck that was any field. So you can define motifs over function fields a la Grothendieck by algebraic cycles also. Do we have such a thing there? Because maybe the standard conjectures for function fields are not needed, and we can circumvent and define the category of motifs over function fields not conjecturally, but like in a correct way, in the abelian category. Is it true?
Well, I mean, the question is kind of very kind of involved question. So you have, well, I mean, the category of motives I talked about, it are some sort of mixed sort of motives because, yeah, the category of C motives. So you cannot form somehow. I mean, you cannot say that you would not have that sort of eigenvalues for Frobenius. So you can say that these are sort of mixed motives, sort of creatures. On the other hand, well, I mean, to trace that why they are the true analogs of that sort of motives. So we have realization functors, and you have somehow the candidates for Shimura varieties. I mean, the whole thing is sort of mysterious also, I mean, to me.
So inside the category of C motives that you define, do we have a pure C motives, a subcategory of pure C motives?
Inside the category of Anderson motives, you have the category of pure motives. So maybe you can, I mean, there should be possible to mimic that sort of constructions of the category of pure motives inside the category of Anderson motives, to perform that sort of categories of pure motives inside the category of C motives. These are all related to
this category is a semi-simple abelian category?
The category of pure motives, I think not.
Pure C motives?
No, I don't think so. No. No. But I mean,
one more question.
But the category of C motives is it's like a Tanakian category.
Okay. And my other question was that you talked about the Hodge theoretic realization of motifs. For the functional case, what is the analog of Hodge theory? What is the Hodge structures over a function field?
So there's Hodge pink structures. They mirror the Hodge realization sort of thing. So yeah, they are called Hodge pink structures. So they are rather lattices inside something, and these are somehow not perfect analogs, but they are somehow, Pink realized that, I guess Hadi should know these kind of things better. Yeah. So
but are these related to the p-adic Hodge structures of say Kedlaya and others?
I don't think so. No.
Okay.
Maybe there would be some relation, but I am unaware of. But yeah, yeah, I have to look at it, or I can, we can Google it and find it. So it's Hodge pink structures are responsible for they're sort of providing sort of generalizations. They are some sort of modifications of the Hodge structure that works our function.
Okay. Thank you very much.
Welcome.
Other questions? Khan Bilgin has a question. Please go ahead.
Thank you very much. First of all, I don't know whether a reasonable theory for canonical models with analogy with Shimura varieties in terms of Rappaport-Zink spaces. So I have two questions. My first question is, in analogy with Shimura varieties, the role of the Langlands-Rappaport set in terms of Rappaport-Pink spaces, Zink spaces. And my second question is whether or not we can express the points on Rappaport-Zink spaces like we did in the points over finite fields of Shimura varieties in terms of effective Kottwitz ripples, like we did in Langlands Kottwitz method.
So maybe you repeat the first question once again. So I was like.
My first question is there any analogy in the Rappaport-Zink spaces for Langlands-Rappaport set, as in Shimura varieties? For example, we assume,
Okay, we have in the Shimura variety setup, so you do the following. So you take let's think of p-divisible groups associated to I mean, your points, like, I mean, let's do like PEL type Shimura varieties. Then you have your points, and you have your abelian variety, and you have your associated p-divisible group. And then you like cook up your Rappaport zinc spaces, and you use these Rappaport zinc spaces like to uniformize your Shimura variety. And then you move your point along the Shimura variety, and you like produce, I mean, you produce this way. I mean, you move on your Newton stratum of your Shimura variety, and then you like, I mean, uniformize them, and then you like, I mean, do like counting points over that. In the analogous picture is pretty similar. So you have your moduli for G motifs, let's say, with G-Shtukas. Then you have your points over there. Then you like, I mean, produce some sort of Newton stratification of that sort of guys. And then you perform, you like, I mean, cook up Rappaport zinc spaces. You use them as like sort of uniformizing space for these guys. And you move, you walk out all through your moduli space, and you like, I mean, take care of all these sorts of things. And then, so you have like two different sorts of, I think, I mean, yeah, the shape is, I mean, quite similar. So what else we have? So then we have, I mean, for both sides, so you have like the local model theory. The good thing here is that, I mean, you have like, I mean, a very neat interpretation of your local models. I mean, we have like constructed local model in two different ways, but so one like corresponds to the sort of so that sort of Beilinson sort of dream field, and let's say Warshawski type of local models, which works globally. And then you have also this analog of the Rappaport zinc local model also as well. So the local model I explained is like the Rappaport zinc version of the local model for moduli of G-Shtukas. And then what else one can say? So I mean, all things, I mean, like, I mean, there's like a perfect analogy, seemingly. The thing which makes, I mean, the point that I mentioned with the category of C motifs, that here you have to pass to some sort of function, to some sort of algebraic closure. I mean, one subtlety that exists over function fields that does not exist in the other side is that, I mean, here you can raise some matrix and it becomes semi-simple, while it is not. But it is not possible in characteristic zero. I mean, this is like one major thing. The other thing is that, like, I mean, the motif you are parameterizing here are not pure, as Amir just also, I mean, mentioned. So, and what else? I don't know. I mean, whether I mean, this sort of description made any help or not.
Okay. Thank you very much.
Thanks to you also. All.
Any other questions for Esmail? Okay, if not, let's thank Esmail again. And so, Ilhan, do you want to start the recording, please?